Section 9.3 Dot products. In this section, we introduce a product of vectors that use a scalar and use it to find the angle between three-dimensional vectors. The dot product of vectors v1, v2, v3 and w1, w2, w3 is v1 multiplied by w1 plus v2, w2 plus v3, w3. The dot product is also known as a scalar product because it is a product of vectors that gives a scalar, that is, a real number, as a result. Sometimes the dot product is called the inner product. For example, find the dot product of two vectors 3, 7, minus 2 and 0, 4, 1. Notice that the dot product is denoted by the small point. We multiply each pair of x, y, and z components and then take the sum of them. The result is 26. The dot product in R2 may be carried out similarly. Given two vectors 3, 0 and 0, 4. The dot product of these vectors is the sum of 3 multiplied by 0 and 0 multiplied by 4. The result is 0. The dot product may be used to compute the angle between two vectors. We have the formula. The dot product of v and w equals to the product of the magnitudes of u, the magnitude of w, and cosine theta. In this formula, theta is the angle between v and w. It is the angle between 0 and pi that is formed when the initial points of the vectors are at the origin. From this formula, it implies that the cosine of the angle theta may be computed as the quotient of their dot product to the product of their magnitudes. When theta equals 90 degrees, cosine of theta is 0 and the dot product is 0. So the dot product is 0 if and only if v is perpendicular to w. Before we can apply the dot product to geometric and physical problems, we need to know how it behaves algebraically. Some of important general properties of the dot product are the magnitude of a vector, the commutativity, and the distributivity. To compute the magnitude of a vector, v, we take the dot product of v with itself. The commutativity says that the dot product of two vectors v and w does not depend on the positions of v and w in this product. The distributivity says that the dot product of a vector u with the sum of v and w equals the sum of two dot products of u, v, and u, w. We take an example. Find the angle between two vectors 3, 7, minus 2 and 0, 4, 1. First, we compute the magnitude of the two vectors. The results are square root of 62 and square root of 17. Then we compute the dot product. The result is 26. We get the equation 26 equals square root of 62 multiplied by square root of 17 multiplied by cosine theta, where theta is the angle between two given vectors. We can find cosine theta and then compute theta as cosine minus 1 of 26 divided by square root of 62 multiplied by square root of 17. Now we talk about the projection of a vector on another vector. Let v and w be two vectors in R2, drawn so that they have a common initial point, as shown in the figure. Let's think about the projection when we have the sun. If we draw a perpendicular from the head of v to the line determined by w, we determine a vector. This vector is called the vector projection of V onto W. This vector is the length of the right triangle in the figure, so it equals to the hypotenuse, which is the magnitude of V, multiplied by cosine of the angle between two vectors, and multiplied by the direction of W, which is given as W divided by the magnitude of W. This formula can be written in a more convenient form using dot product. Using the dot product, we express the magnitude of V multiplied by cosine theta as V multiplied by W divided by the magnitude of W. The dot product of the magnitude of W to itself equals to the dot product of W with itself. By taking out the direction of W, which is W divided by the magnitude of W, from this formula, we get the magnitude of the projection. It is called the component of V along W, also called the scalar projection of V onto W, and equals to the dot product of V and W divided by the magnitude of W. For example, find the vector projection and the component of V along the x direction. Recall the formula for the projection. The projection of V onto W equals the dot product of V and W divided by the dot product of W with itself and multiplied by W. The projection of V onto I equals to V dot product with I divided by the dot product of I with itself multiplied by I, which gives 2I. The component of V along W is computed as the magnitude of the projection, so the component of V along I is 2. One important application of the dot product and projection occurs in physics when calculating the amount of work done by a constant force. When a constant force is applied to an object through a distance d, the work performed is defined by the product of force and distance. Now we consider force F acting in some other direction and move a particle along a displacement vector d. Then, the work performed is given by the product of the scalar component of F along d and the distance moved by the object. This is exactly equals to the dot product of F and d. For example, how much work is performed by a force vector F equals 4, 5, 3 by moving a particle from the point 5, minus 10, 0 to the point 15, 10, 0. Taking the difference of the end point and the initial point, we get the displacement vector 10, 20, 0. To compute the work, we take the dot product of F and D, multiplying each pair of corresponding number, and taking the sum gives 140. If the force is given in Newton and the displacement is given in meter, then the unit of the work is joule. This is the end of this session. Thanks for watching.